Hello everyone, this is Abdullah Mahmud from California Air Resources Board. First, I'd like to thank the organizing committee for giving me the opportunity to talk to you. Today, I'll be talking about estimating population exposures to toxic volatile organic compounds in Southern California, utilizing the CMAS model version 5.3.2. Before I start, I'd like to acknowledge the contributions from my colleagues at ARB. They are Ping-Kwan D, Melissa Vanessek, Roger Koch, Winley Young, and Jeremy Evis. Here is an outline for my today's talk. First, I'll give a little background of the study. Then I'll talk about the methods, present some findings, demonstrate model performance, and finally, I'll summarize my talk. According to the California Health and Safety Code, a toxic air contaminant (TAC) is an air pollutant which may cause or contribute to an increase in mortality or an increase in serious illness, or which may pose a present or potential hazard to human health. TACs are often called air toxics. In the past, several air toxics programs were enacted in California, such as AB 1807, which requires the state to reduce public exposure to air toxics, and AB 2588, which requires stationary sources to report the types and quantities of specific toxic pollutants their facilities routinely release into the air. More recently, in response to the Assembly Bill 670, California Air Resources Board established the Community Air Protection Program with an objective to reduce exposure in communities that are most impacted by air pollution. Let's talk about model setup and simulations. The figure below shows two modeling domains in Southern California that are considered for the current study. The bigger domain that encompasses the areas under South Coast AQMD has an extent of 212 by 80 grid cells, and the smaller one covers the San Diego County APCD and has an extent of 68 by 70 grid cells. Both domains have 2 km horizontal resolution. Modularity emissions were generated by combining emissions from biogenic sources, area and mobile sources. Point source emissions were generated during CMAS inline processing. Simulations were carried out by two sets of emissions scenarios. The first one included emissions from both US and Mexico, and the second one included emissions from US only. This was done so that contributions from Mexico emissions to total cancer risk can be estimated, particularly in San Diego County. The meteorological parameters were prepared from the warp output. SAPRAC 07 TC chemical mechanism and ARO 7 aerosol module were used in the CMAS model. Large-scale output from CAM model simulations conducted at NCAR was used to drive the statewide 12 km runs, and output from the 12 km runs was used as boundary condition for the 2 km simulation for each domain. The simulation was conducted for a whole year for the year 2017. In this section, I'll talk about some of our findings from both San Diego and South Coast air basins. CMAS produced hourly concentrations were first converted to daily average concentrations, and later daily concentrations were converted to annual average concentrations. Annual average concentrations were applied to calculate cancer risk at 30-year exposure level for individual species, and calculated risk from individual VOCs were then summed to get the total toxic VOC cancer risk. Model annual/daily average concentrations of measured toxic VOCs were compared to measured dataset available for 2017 to demonstrate model performance. The table contains the list of measured toxic VOC species that were considered for risk estimations in the study. These are acetaldehyde, formaldehyde, 1,3-butadiene, benzene, paradichlorobenzene, perchloroethylene or PERC. The 1,3-butadiene has the highest cancer potency factor, followed by benzene. Note that, in addition to cancer potency factor, levels of toxic VOC annual average concentrations and population in a modeling grid cell determine the level of cancer risk from exposure to air toxics. Now let's talk about the results from the San Diego County. As I mentioned earlier, for this domain, simulations were carried out using two emissions scenarios. One included emissions from both the US and Mexico, and the other included emissions from US only. The table here lists all the species of interest and their emissions under different emissions scenarios. Note that the combined emissions from both US and Mexico is much larger than the emissions from US only. In this slide, what we see are the two plots of benzene annual emissions in tons per year. The left one is the emissions from both US and Mexico, and the right one is emissions from US only. Note that benzene emissions are much higher near the border areas in Mexico compared to the adjacent areas in the US, as you can see from the plot on the left. Here we see two plots of benzene concentrations. The left one was generated under the emission scenario where both US and Mexico emissions were considered, and the right one was generated under the emission scenario where only US emissions were considered. Note that the concentrations of benzene are much higher, almost 2 times, particularly in areas near the US-Mexico border. This clearly shows that the impact of cross-border transport of toxic VOCs. The table contains the population-weighted 30-year exposure level VOC cancer risk for the San Diego County. It lists all the species and their relative contribution to total cancer risk per million under two different emissions scenarios. Emissions from outside the US could contribute as much as 10% to the total cancer risk from toxic VOC in San Diego County, as you can see from the table. However, the contribution from emissions outside the US could be much higher in communities along the US-Mexico border. Also, note that the emissions estimates in Mexico are highly uncertain, which will also translate to uncertainty in the risk estimates. In this study, we are also interested to learn about the contribution of secondary formation of toxic VOCs. The table here contains the contributions of formaldehyde and acetaldehyde to 30-year exposure cancer risk under two different emission scenarios. Secondary formation of acetaldehyde and formaldehyde in the atmosphere through chemical transformation contributed as much as 70% of the total individual cancer risk for both VOCs in San Diego County, as you can see from the table. Now let's move on to the South Coast Air Quality Management District simulations results. In this slide, what I'm showing are the plots of distributions of population on the left and the annual average concentration of formaldehyde in ppb on the right. Calculations of population-weighted cancer risk depend on the distribution of population and annual average concentrations. There are about 15.6 million people live in the SoCal. Like in the previous slide, distributions of annual average concentrations of toxic VOCs are also shown here for 1,3-butadiene, acetaldehyde, and benzene. The table contains population-weighted annual average concentrations for toxic VOCs, where formaldehyde has the highest concentrations, followed by acetaldehyde and benzene. The table shown here contains the estimated population-weighted 30-year level individual toxic VOC cancer risk and the total toxic VOC cancer risk for the South Coast Air Basin in 2017. The total VOC risk is about 129 per million, in which benzene has the highest contribution, followed by 1,3-butadiene and formaldehyde. In the next few slides, I'll be showing model performance demonstration for the South Coast simulation. The measured data were obtained from CARB's toxic VOC database. Only 3 PAMS/SLAMS sites within the South Coast modeling domain reported measured data for major toxic species in 2017. The sites are Azusa, LA North Main Street, and Riverside Rubidoux. The data were reported typically in every 6 days. Model performances in predicting concentrations of total PM2.5, elemental carbon, and 8-hour ozone were also carried out for several sites in the SoCal, but findings are not presented here. The map here shows the locations of the 3 monitoring sites where the data were reported. The sites are sparsely located in the valleys, as you can see from the plot. This slide contains the charts that show the model versus observed annual average toxic VOC concentrations for 3 monitoring sites. Toxic VOC's concentrations are predicted relatively better at the LA North Main Street site compared to 2 other sites located at Azusa and Riverside Rubidoux within the SoCal. The model predicted formaldehyde concentrations much lower than observed at all 3 sites. Column integrated model concentrations will be further compared to satellite data in a future effort to evaluate the model performance in predicting formaldehyde concentrations. These plots here show examples of how daily concentrations of acetaldehyde varied throughout the year. The model did a decent job at the LA site compared to the site at Azusa in predicting 24-hour average concentrations of acetaldehyde. Just to summarize, toxic VOC air quality modeling for the South Coast and San Diego County in Southern California have been completed for 2017 emissions. Secondary formation of toxic VOCs in the atmosphere such as formaldehyde and acetaldehyde could contribute as much as 70% of the total mass concentrations. Communities near the US-Mexico borders are likely to be impacted more by toxic VOC emissions from the other side of the border, and they contribute as much as 10% to total 30-year exposure cancer risk due to inhalation exposures to toxic VOCs. The CMAS 5.3.2 performed relatively well in predicting toxic VOC concentrations compared to available measured data for 2017 within the modeling domains. Other sources such as satellite of observed data as they become available will be compared to the model data for Southern California domains to demonstrate model performance in future efforts. Toxic VOC air quality modeling is also underway for San Joaquin Valley and Northern California domains. And this concludes my presentation. Thank you very much for listening. I'll be looking forward to your questions and comments during the discussion session. Hope to see you soon. Thank you again.